Okay, so in the HL portion of biochemistry, you've got to look a little bit more closely at enzymes, and specifically the concept of inhibitors, how they interact with enzymes, and some specific effects they have on the enzyme kinetics. So, inhibitors is a term that's used for a variety of different kinds of chemicals. Could be organic, could be inorganic heavy metal ions, could be smaller polyatomic ions, could be antibiotic molecules. Lots of different things act as inhibitors on enzymes. That's how they carry out their functions. Um, Inhibition is usually irreversible because the inhibitor will actually form covalent bonds, which, as we said a couple times now, are considered to be pretty much permanent in terms of the enzyme. So if you bind permanently to the enzyme, you're going to essentially render it no longer capable of working on the substrate. There's two categories of inhibitors. If we compare this picture being normal enzyme substrate action, where the substrate fits with the enzyme, they induce a fit with one another, and then the products leave. In competitive inhibition, the competitor, whatever the molecule is, also binds at the active site. And so both the substrate and this other competitor inhibitor are competing for the active site. Okay, but if the competitor gets there and binds permanently with that active site, it now inhibits the actual substrate from binding with the active site. So it's pretty straightforward, intuitive name. The inhibitor is going to compete for the active site and block the substrate from reacting there. A non-competitive inhibitor is one that doesn't bind at the same active site. It binds at another site on the enzyme that's known as the allosteric site. And in doing so, it causes a sort of a ripple effect of intermolecular attractions in the enzyme, which end up changing the shape of the active site, even though it's not directly binding there. And that means if you change the shape of the active site, then the substrate no longer can fit there and bind there, and that's how it inhibits the action of that enzyme. Heavy metal ions are usually thought to act as non-competitive inhibitors. They don't necessarily have to bind to the active site, but their positive charge and the covalent bonds that they form with the enzyme at other sites is so influential that it can change the shape of the active site permanently, and therefore render the enzyme completely ineffective anymore. There's also a specific kind of inhibition that's known as product inhibition, which is pretty cool. And it explains how some feedback loops could work in the body, specifically negative feedback loops. So this is a special case where one of the products of a specific metabolic pathway actually ends up acting as an inhibitor for an enzyme earlier in the process. So if you look at this diagram, A gets turned into B, gets turned into C, and so forth. And eventually, the fifth or sixth step down the road, you've made this product G, and G turns out fits and can bind to this enzyme, which was responsible for turning C into D. And so as a result, it's going to change the shape of this key enzyme, which will effectively stop the conversion of C to D. If you do that, you're eventually going to stop the production of G. So, this could be an example of something like in a hormone cycle, where once a certain amount of a particular hormone has been made, it also, in addition to being able to do its job, send a message throughout the body, some of that hormone may actually, as it circulates through the blood, prevent the production of more of that hormone. And that way, it's a way the body has developed naturally to keep levels of that hormone in check and only getting to a certain level. And it's a pretty ingenious way to have negative feedback. So a product can actually inhibit an earlier step in a metabolic pathway to prevent too much of that product being formed. Okay, a couple of terms that are for the HL kinetics units with enzymes are the Vmax and the Km value. Vmax, fairly intuitive term, V for velocity and max for maximum. So it refers to the maximum velocity or the maximum reaction rate that an enzyme can give you under given conditions. So that's that sort of saturation point when we keep upping the substrate concentration. Eventually, you reach a point where you can't go any faster, and that would be the Vmax value. It can vary a great deal for different enzymes, and it's greatly influenced by things like temperature and pH, for example. Um, Now, this other value, the Km, or the Michaelis constant, is the substrate concentration when when the rate is half of Vmax, or half that maximum rate. So it's the substrate concentration when whatever the rate is equals half of the Vmax. And this Km constant, it's pretty cool. It gives you useful information about the effectiveness of an enzyme at low versus high substrate concentrations. So, for example, if something had a low Km value, that would mean that the enzyme reaches half of its maximum rate, even when you have very little substrate around. And what that means is that the enzyme is probably going to be very easily saturated, and whether or not the substrate concentration changes, it's probably not going to affect the rate of the reaction all that much. And you can see that on a graph down below that compares two different enzymes. The one in red has a low Km value, so it reaches half its reaction rate at very low concentrations of substrate, and so for the most part, it's always going to be operating at its maximum speed. Whereas something with a higher Km value, it takes longer for it to reach half of its max rate, which implies that as you change substrate concentration around, this enzyme goes from acting very slowly to having very high reaction rates. So it can respond to changing substrate concentrations. And so different enzymes have different roles in the body. Some need to be able to respond to changes in the environment, and some need to just keep chugging along and doing whatever their reaction is at a steady rate. And so different enzymes will naturally have different Km values depending on what their role is in the body. One thing to point out here that people sometimes get mixed up: Vmax is a rate and Km is a concentration. Okay, so Km is the concentration of substrate at which you have half the Vmax, whereas Vmax is just the maximum rate of reaction for an enzyme under certain conditions. So the effect of the different inhibitors, the competitive and non-competitive, on Vmax and Km values. So we've got the sort of standard shape for our enzymes. We know it sort of goes up relatively quickly at first, and then it's going to plateau at Vmax. And I apologize for the messiness of that curve. So this is the original Vmax value over here. And so now the question is, well, I guess I should write in Km too. So if that's Vmax, then here's about half. So here is Km, the concentration that gives us half of Vmax. Okay, now if you have a competitive inhibitor, it's going to compete for the active site. But what that means is if you get more and more substrate, and they're both sort of fighting over the same active site, eventually, if you have more and more substrate, the substrate can outcompete the competitor. Therefore, at a certain substrate concentration, the inhibitor can have almost no effect. So as you get more and more substrate concentration, the impact of the inhibitor gets less and less, and you can actually eventually make it to this original Vmax if you have a high enough substrate concentration. So the rate is affected, it is lowered by this inhibitor, but eventually you can make it, if I get off my screen here, right there, you can eventually make it to the same Vmax. It just takes a higher substrate concentration to get there because you've got this other thing that's competing for the active site. So for a competitive inhibitor, the Vmax is the same, but if this is the same Vmax, it's now going to take us longer to get to this halfway point. So it's going to take us all the way out here. So now this is the new Km. So Km is affected by competitive inhibitors, but Vmax is actually not affected. You can eventually reach the same Vmax. It just takes a higher substrate concentration. With non-competitive inhibitors, though, it's a little bit different. They don't compete for the active site, so the rate is definitely lowered, and no matter how much substrate you have, it doesn't matter because you can never reach that same Vmax again because you're not competing. So there's just a certain number of enzymes that are going to be taken out of the playing field, really, and can't react with substrate anymore. So a non-competitive would be sort of lower, and it would also plateau off at a lower Vmax. So this is a new Vmax here for something with a non-competitive inhibitor. So a non-competitive inhibitor actually lowers the maximum rate of reaction because there's no way for the substrate to outcompete the inhibitor. It just renders many of the enzymes ineffective. As a result, though, because this is the new Vmax is a lot lower, half the Vmax ends up being much lower as well. And so the Km value for what gets you to half Vmax ends up actually being the same. Now, this is a pretty rough sketch, so that might not be entirely true in this drawing, but it's supposed to be that because now the Vmax is lowered, so is half Vmax, and so Km actually ends up staying the same under non-competitive inhibition. So in summary, competitive inhibitors go for the active site. Therefore, Vmax isn't changed because eventually with high enough substrate concentrations, you can get to the same Vmax, but it makes the Km much higher. It takes a lot longer to get to that half of the Vmax. For non-competitive inhibitors, the inhibitor is binding with the allosteric site. That lowers the Vmax because many of the enzymes are permanently rendered ineffective and can't be outcompeted. But because Vmax is lowered, Km actually ends up being unchanged. So for each one of the types of inhibitors, one factor remains unchanged and one is affected. I'm not sure how you're going to remember which is which. We'll have to think of a good reminder about which is which. But I guess I find the competitive one, to me, makes sense that eventually you can outcompete the competitor, and that means that the Vmax is unchanged. And so if I can remember that Vmax is unchanged in competitive, that means Km is unchanged in the other, and I can probably figure out the remaining two changes. And so that's the HF portion of the kinetics topic. You're specifically looking at these inhibitors and things like Km and Vmax. So down here, this is the list of topics for the HL portion of the enzyme topic, as well as some of those other topics that we've covered in previous videos.